All right. Now we're gonna start getting into the stuff that like the rest of the semester's on. This actual direct topic is not on the final, but it is. Like a supporting structure for that, so like. Understanding chapter 8, like chapter 8 explains why we're gonna be able to do all the rest of the shit that we're gonna be able to do. Chapter 8 and stats. Math 21 is on sampling distributions. It's all bright. It's so fucking bright. So, back in spring of 2022. Not 2022, 2020. The year of the glorious pandemic, right when the world changed. We had classes until like March and then COS shut down. But before that, I had 3 stats classes. Were on my teaching schedule. At the end of the semester. The mean score or grade, I'm gonna say score, because grade sounds like a letter and this is all based on numbers. The mean score for each class was different. Not greatly different, but enough. I don't remember the actual exact value, but like if one was 73.1, another one was like 72.7. You know, things like that. So these were 3 sampling means. 3 means from samples. And since the mean for each sample can be different and is different. It means that, or. I hate that we use the word mean as average, and then we have another definition of the word mean. Let me think of another word that doesn't use the word mean. Since the mean for each sample can be different. This implies. That the sampling mean, or the sample mean. Is a random variable. Chapter 6 and 7 were on random variables. And since it's a random variable. It has a probability distribution. Like we did when we had like the binomial distribution. We had Poisson distributions, we had a bunch of different distributions. It's gonna follow a distribution, we don't know which kind. Usually something like this is like a normal distribution, but. We'll take a look at what's going on here. And we can approximate. That the mean. Of the sample is approximately the mean of the population. And the standard deviation. Of the sample mean. Is equal to the standard deviation of the population. Divided by the square root of n, which is the sample size. I'm gonna, in our first example, we're gonna do an applet that does a simulation on StatCrunch. But in the first example, let's look at IQ. And we know that the mean of the population is 100. And the standard deviation of the population is 15. So if we look at like a sample size of say 9. If we use 9 people for our mean. The mu of our sample should still be approximately 100. It's gonna be close. And the standard deviation of our sample should be 15 divided by the square root of 9. 15 divided by 3 is 5. And it's not gonna be exactly equal to, but it's gonna be really close. There's always variation with population or sample. That's the approximately one, the rest, those other 3 are equal. If I do n equals 25, we'll look at both versions. The mean of that sample should still be around 100. But the standard deviation of the sample should be 15. Divided by the square root of 25. Square root of 25 is 5. 15 divided by 5 is 3. We'll take a look at both of these on StatCrunch. Just a sec. Almost ready. It looks so ready. All good? All right. Let me okay, I'm gonna load up StatCrunch. I'll do view the StatCrunch website. And I'm gonna do applets sampling distribution. If you want to explore this later on, you're welcome to. That way you'll know what I'm doing. It's fun to play around and look at what's going on. So if I do applets and then sampling distribution, it gives me some options. I'm gonna tell it it's bell-shaped. And we're gonna do 100 was the mean and standard deviation was 15. That's our IQ. We'll come back and look at uniform and the other ones in a second. Zoom bar is getting in the way, there we go. Okay, so this is the mean and standard deviation, like this is a sample group. I'll say sample size is 9 here first, we were talking about 9. And let's just see what one time happens, it's picking 9 people around doing it, and it got a mean of 96.9. Standard deviation showed 15, that's not great, but that's only one sample. Let's do that. Is there a way to speed this up? Speed it up. Going all slow. So we have standard deviation is changing each time, but when we look at the sample means down here. This is an individual sample, when we look at the sample means, let me do 2 more. So that I have 7 samples. Or 9, sorry, 9 samples. This is not quite 5, but it's close. That is not quite 100, but it's close. Is there a way to speed this up? No. You can see it's building, it's making a probability distribution. But it's doing it as a bar plot here, and it finds the sample mean of 9 people, then it's building a sample of the sample mean. I wanted to get up to 25. Which means watching this a couple more times. God, it's going slow. Oh my God, it's gonna, fuck. Wow, standard deviation is 17. So like some of them are gonna have big standard deviations like this. If I go through, do one more. We're still around 25, and since our sample size is 9, the standard deviation is still around 5. So it didn't matter how many of those I do, if I do 1,000, there goes super quick and it builds up really quickly. If I do a couple thousand like that. Now it's showing me a sample size of 9 when we have a lot of them. The mean is really close to 100, and that's really close to 5. So an individual one might be way off, like this one has a score that's almost 140. Which is genius level. Like 130 is above 2 deviations, so it's like genius level, but when we average out this group. That really high score, I don't know, 137, 38 or something like that. It gets kind of like smoothed out with the other ones, so like the big outliers don't have a huge impact. I do reset and we do 25 at a time. And I'll do a couple thousand. That's got a really low one of like 70. And then like a really high one in like almost 130. But with enough samples. The mean is close to 100, and now the standard deviation is close to 3, which was 15 divided by the square root of 25. And it's based on the sample size here. When we do just one, oh, good, if sample size is bigger than a certain value, it just kind of goes quickly. If I just do a few, it's a little bit further away. Like 2.8, that's not as close to 3 as it was. But the more times I do it, see, 2.7 is getting even further, but I only have 21 different samples I've done. This is like having a class size of 25 and finding the mean of all their test scores. Do it a few times, wow, I got as low as 2.5 for a second, that's really low. 3.4, it's still really low, or it's a lot higher than the 3. Relatively, 3.4 compared to 3 doesn't sound like a lot, but it's like over 10% higher. But if I do it like 1,000 times. Now these start balancing out to 103 really quickly. And it doesn't vary much. If I do sample size of 100. Then we're dividing by the square root of 100, which is 10. 15 divided by 10 we should get a standard deviation of 1.5. I'll just do one at a time for a second. That's quite a bit lower than 1.5 considering. That's like percentage wise, it's a lot lower than 1.5. So only doing it a couple times or even, wow, 0.98 is even further. And it can go back up above. It can come back down to 1.5-ish. But as we do a lot of them, it starts balancing out to 1.5. And the mean starts balancing out to 100. Look at the decimal places now. If I do 20,000, 100, 1.00, mean and median. And at least, well, almost 2 decimal places. If we round it, it would be 1.51. It's still really close to it. There's a property why that's happening. We did the little piggies thing in here, didn't we? Yeah, we did the piggies thing. And we showed like what happens when the numbers get larger. When n gets big enough, it stops changing much. This is another example of seeing the law of large numbers take effect. When we only have a few at a time, we get quite a bit different. Not quite on the money. Wow. There we go. Like only doing a couple. The mean's still gonna be pretty close, but the standard deviation shows a lot of swing in it. The law of large numbers kicks in when we do a lot, and everything starts balancing out. And it starts ricocheting around 1.50. What about the other distributions? Let's go look at uniform. Let's do like a lower bound of 0 and an upper bound of 6. That's kind of like rolling a die. And so like this is 0 to 1 is rolling a 1, 1 to 2 is rolling a 2, 2 to 3. Does it have? Yeah, it's just uniform. Okay. If I do this, what happens? Notice, actually, I'm gonna go back. Let's go back to that real quick. Make that 9. Oh, let's make it 4. We're doing, this is the distribution or the probability distribution of a bunch of samples from a standard distribution. So we started with the standard distribution of IQ, and our sample mean has a sampling distribution that looks like a normal distribution as well. Notice what happens when we start with a uniform distribution. Damn it. Nope, we'll just start over. Say 25. Okay, it's not a whole lot going on there. But if I do 1,000, get this up to 20,000 like we had before. 20,000. Our uniform distribution, the rolls that we're getting. This is like rolling 25 dice. And finding the average of the 25 dice. Some of them are really low, like getting an average of 2 on 25 dice. That's fucking hard, that's rolling a lot of ones. Maybe a couple, maybe a lot of 1s, 2s and 3s, but nothing higher. We also have ones up near 4, which is rolling like a lot of 4s, 5s, some 6s, but stuff like that. But most of them are near the 3. And that's like taking the average of the 25 dice and doing it and making a distribution of all those. Even a uniform distribution, when we do this sampling distribution of a mean. It makes this normal distribution. We could do right skew, there's another way to show right skew, this is kind of neat. If you use like I hold down, like see the cursor there? If you're playing with the uniform and you hold down the mouse button. You can guide it so that it makes the distribution. So I'm making a right skewed distribution right now. My own custom right skewed distribution, I don't know what the equation is. But it's definitely not symmetric, it's not bell shaped. And it doesn't really look that great to start with, but if I start pumping it up to a couple thousand. It's going to bell shaped as well. Another way of seeing this so that you can see it a little better. I have 20,000 rows. And we went up to 25 person in each sample. So each row is like a sample of people. This is like the scores of the IQ for them. 25 people, this is that, like, let me go up to the first row. The first row, we got 25 people, second row, we got 25 people. And if I look at the mean of the first 9 people in each row, I get something like this. Some of them are low, 90. That's because I've got scores like 69. Oh wait, that's not the first 9. First 9, I've got an 81, I've got a 75, I've got an 80. I've got a bunch of low numbers. I found the dumb shits of the group in this distribution here. Another group will have really high, 116 is pretty high. What does that row, what is that row, 7? The first 9 people in the 7s, we've got a 137, we've got a 122. We got another one almost in the 130s, a 120. This is a group of super smart people. So like when we take the mean or like get a sample, we don't know what we're getting. Each group will have its own mean and standard deviation. So like this doesn't match those two I just showed. Row number 2 and row number 7, those groups are drastically different than the population. But if I take them all, instead of looking at one group, do a whole bunch of groups and take the mean of them, I can do stats. Now I've got it as a column. I can do stats, summary stats, columns, come down here and look at mean 9 and look at the mean and standard deviation here. And now we see it balance out. So those big groups kind of get smoothed out by all the average groups. It kind of, when you do this, these sampling distributions like this, it kills outliers. We still get a normal distribution though, as we saw on the applet. So. And I'll write down what I was using in case you wanted to look at it later, the applet. Sampling distribution, you can play around with it. And we looked at a distribution. We looked at a normal distribution with the IQ. We looked at a uniform distribution with dice. And we looked at a skewed right distribution that I made up. But I could have put a Poisson distribution in there or something like that. And we saw that when n was large enough, they all looked like a normal distribution. This is one of the most important theorems in all of statistics. It's called the central limit theorem. It's right up there with importance next to the law of large numbers. Regardless of the shape, of the underlying distribution. The sampling distribution of the sample mean is approximately normal. And we gotta add a caveat, because it wasn't normal. Didn't look all that great when we had a low number of them. For large enough n. Why do we like this? Well, a couple things. A normal distribution, we can always use the empirical rule. If we have a mean and a standard deviation to figure out the empirical rule chart. You know, our 68%, our 95%, our 99.7%. Or plus or minus one deviation, plus or minus two deviations, plus or minus 3 deviations. That's pretty good. It also makes it so a lot of hypothesis testing. Relies on something being normally distributed. What chapter did we start doing hypothesis testing? I think it's chapter 10. Yeah, chapter 10 is hypothesis testing. Even next chapter, chapter 9 is on confidence intervals. Having a normal distribution is gonna make it so we can use the same strategy to determine whether something is reasonable or not. For a variety of different setups, a variety of different underlying distributions, different sample groups, different types of questions. And we can use the same strategy on all of them. It's called doing like testing alpha versus a p-value. If we didn't have this, we have to use a different distribution and follow different stuff, and then you gotta pull out the shitty formula and all that. Figure it out, but if it's a normal distribution, the good stuff happens, the magic happens. So what is large enough n? Different books say different things. I believe ours says n greater than or equal to 30 now. It used to say 40. The homework is gonna drive you about crazy. Cause it's gonna give you the mean and it's gonna give you the standard deviation of the population. And when you're not paying attention, it starts, it asks a couple questions about that. And then like part C or D sometimes, all of a sudden it says, now you have examples group of size so and so. And you have to remember on the homework problems. They'll give you. The mean and standard deviation of population. When they give you a sample size. Standard deviation has to change. Standard deviation of this thing is the standard deviation they gave you. Divided by the square root of that sample size, whatever they gave you. So you're gonna have to do a little calculation in your calculator. And you're gonna forget at first and you're gonna go, what the fuck? And it'll be like, it'll say like if it has IQ, it'll say this, the standard deviation is 15. And then you're gonna get down later on, and it'll be like all of a sudden it's 5. And you're gonna be like, bullshit, it fucking says 15 right there. And you're saying you're gonna email me why, but this is why, you're dividing by the square root of sample size. You will see when we do the hypothesis testing and confidence intervals, I'll show you. This is just the way we do the testing, it shortcuts. Using the normal calculator. I'll even show you doing this stuff with the normal calculator. Like in StatCrunch. We'll do a problem using the normal calculator, and then we start doing hypothesis testing, it does all the normal calculator work for you, but until you get to that point. They're gonna have you using this information in the normal calculator. And now that you've shown it's a normal distribution. Says that it follows the central limit theorem, they'll ask you. Is it approximately normal? If n is big enough, if n is bigger than 30, you can say, yeah, it's approximately normal. And since it's approximately normal, you can use the normal calculator, and it makes it all fine and dandy for finding shit. That's what 8.1 is on. So 8.1 was on the sample mean. With sampling distributions of the sample mean. And I will recap the. Formulas you need for that right now, just so you can have them all next to each other. For the mean one, when you're working with the mean. Our sampling distribution matches the population mean. But our standard deviation. Has to be the standard deviation of the population divided by the square root of n. Said that a couple times. The part that's changing is what's in 8.2. Eight point two does the sampling distributions. For a sample proportion. I have to go back and do this, because I did the sample mean for my 3 stats classes. I should go back and get them, should get the data. I have access to it, I can calculate that, I have it, I save all the Excel sheets where I make calculations and shit. I could have just as easily done a sample proportion for each of those, like the proportion of students that passed. Not just what the average grade was, but the proportion of students that got a C or better. I could have done that just as well, and it has its own strategy. But again, since we're doing a bunch of them. We're gonna look at the sample mean. Of proportions. So this will be equal to the actual proportion. And you'll have that from your. Either they give it to you, or we can use x over n. And then standard deviation for proportion problem. Is the square root of p times 1 minus p over n. Finding the mean of a population. The entire population is relatively easy. We saw with the law of large numbers, if you go large enough. The value stops basically changing as you add new people. Sample proportion though, like the proportion of a population. That maybe has brown eyes, or the proportion of the population that has blue eyes. That's a little harder. Every sample is so completely fucking different, we could have a group of all, we could go over to. Germany in World War II, and we've got a lot of blue-eyed people we're looking at in the army. And you would say the proportion of people with blue eyes is high. But you go anywhere else in the world, the proportion is completely different. So finding that sample or finding the proportion for a population is extremely difficult. Because you have to survey everyone. I'll say all of them in case it's not a person. But finding the proportion for a sample is easy. P is X over N. The people that have what you're looking for. Over the number in the group. We did this. This was very similar to calculating relative frequency. We did this with probability. We've done this a lot. How many of you have seen the first Star Wars that came out, episode 4? Only a couple of you, okay. Well. Do the rest of you at least know who Luke Skywalker is? Like at least recognize the name? Every semester, this number gets lower and lower, and pretty soon, one of these days, I'm gonna get nobody's fucking seen Star Wars. And then I'm gonna feel old as fuck. I asked people. What do you think of Luke Skywalker? In the first movie, episode 4. And I gave them some options to pick from. I said whiner. I said hero. Or heroic. I said not applicable. And I said other. And now either everybody in the class that I asked this from had seen it, at least the people that were present on the day, or had seen enough to form an opinion, or like they didn't want to put themselves in the NA group or other group because they didn't have opinion. I had 33 people say he was a whiner. I had 9 people say he was heroic, and the other categories were 0. So if what I'm looking for is the proportion of the population, proportion that thinks he's heroic. Is the number that saves her up, which was 9. If I calculate the total here, 33 plus 9 is 42. Out of 42. And we give this a hat. In fact, we call this p hat. That's what it's called, p hat. The little hat. In statistics, this value is called the point estimate. It's an estimate of the proportion of the overall population. Okay, so. We do the same type of sampling distribution thing that we did with the mean. We find the proportion of a group, but then we find a proportion of a bunch of groups. Because we know we might have just asked all the fucking smart people, did you pass the class? And they said, yeah, and we think like the overall pass rate is high. So we don't look at just one class, we look at like all the classes. As many as we can. So. We want. The sampling distribution. Of the sample proportion. To be approximately normal. Just like we had with the sample mean. Sample mean one was pretty easy, just do enough different groups and you have what you're looking for. This one, there's a little bit more to it. We had to. For this to be true. Or we'll assume true. That should be true. Because we can plot it on a graph. We want n times p times 1 minus p needs to be greater than or equal to 10. That's our first criteria. And our second criteria is the sample size needs to be less than 5% of the population. Second criteria. So this is our sample size. And big N is population size. So that equation says sample size is less than 5% of that. let's call that A and B. If A and B are met, we have a normal distribution. And to do any stat calculations, we can do stats, calculators. Normal. If one of these is not met. Use the binomial calculator. Homework problems will make you test those two criteria. While you're writing that down, let me see if I can find a couple good ones in the chapter 8 review. Now, we can take a 10-minute break if you like, or we can go for another 15 minutes and call it a day. Does anyone need a break right now? Is everyone good for the 15 minutes? All right, let's do it. Keep going. So let me. Alfredo, you're good to keep going, or is that a yes, I need to go pee? He thinks he gets a vote, even though he's at home.
Sounds like takes the computer to the restroom.
He said, let's keep going. All right, so I opened up the chapter 8 review homework. And hopefully I can annotate on the screen. Look, good, I can. So like for one, the ones that start with 8.1 and then some numbers, you're working on things that are means. Oh, there we go. Okay, now I can scroll. And the ones that start with 8.2 will be proportions. Just looking at one here. For the mean one, we have mu of x equals mu of population. And standard deviation of x is standard deviation of population over square root of n. With that in mind, let me turn off annotate. This is the mean of the mean of the sampling mean. should match the 78, should be the same as the population. So we're gonna say it's the same as the population. And it's gonna ask this, and notice if I try to put in 28. It's gonna tell me to fuck off. But it's gonna tell me what I did wrong if you actually look at it. If you don't just close it too fast, it tells you what you did wrong. What I needed to do is I need to apply this. I have 28 divided by the square root of 49. That's 28 over 7. Which is 4.
Is my box in anybody's way?
No,
Thanks.
I didn't even know it was yours. You need it right now?
No, it's for Mount Twin tomorrow.
Okay,
I'm gonna leave it here for about another week, so I don't have to keep hauling it upstairs and back for the week.
that makes sense.
Thank you.
So we'll check it, it says great. So that's what I meant by like, it will try to trick you. This one, not so bad, it like did it right, it was like right away, just do it. Let's see. Here's one where we can use it. So let me erase part of that. So it says describe the sampling distribution of X. N is above 30, so we're gonna say the distribution is approximately normal. Okay. We wanted N to be above 30 and it is, so good to go. Even though it says the population is skewed right. The sampling distribution when N is large enough is approximately normal. Now they want us to give the values, so the mean will be the one they gave us. Standard deviation is gonna be. Where's my pencil? There we go, pencil. We'll change color real quick. We have, the population was 27. And we're dividing by square root of n, which is square root of 81. That's 27 over 9, which is 3. So I'll put 3 in here. And now it wants us to make some calculations, so what I'm gonna do is go over to StatCrunch. And since we've shown it as a normal calculator, we are going to use the normal calculator. That's really flat. There we go. I'm gonna put in the mean and the standard deviation we have. And they want X is greater than 74.05. Cute. Round to 4 decimal places is that. 0.885. Can't paste, Control V. There we go. And the rounding was already good, check answer. So that's what we're kind of doing here, you gotta go use the normal calculator once you've gotten a normal problem. The rest of these are just changing the way that normal calculator looked. So doing less than or equal to 62.05 or 62.5. We put that in here. And that's what it's asking. Let's go down and find one that's a little trickier. They gave you all the information in the beginning. That doesn't look any tracker here, they're doing all the same things we did before. Let's check out this shit. Let me clear all. So what is the probability that a randomly select, it tells us right away it's approximately normal. How is this helpful? It says it's, oh, this is the one where they changed the shit on us. I'm sure of it. 266 with 16. And they want the probability that it's less than 260. And 4 decimal places, I get that. Interpret the probability of 100 people are asked, we'll move the decimal point over twice for 100 people. Or multiply by 100, we get 35.38. And we just gotta choose the right one. So I got 35.38, let me get that off the screen real quick. If 100 pregnant individuals were selected, we would expect, oh, the thing that's changing is we want it to match less than, less than that one. And how many decimal places, round to the nearest integer was 35. You guys had a problem like this, similar to this on the test. Now they come along and they do 18 human pregnancies. So the underlying distribution was normal, so it doesn't matter that n isn't large enough. It's still normal. The mean is gonna be the same, 266. And this is where they're gonna change that shit up, and we need 16 divided by the square root of 18. 16 comes from there, 18 comes from the random sample size. So it's like out of nowhere, you've gone through a couple things, they changed some shit up. I'll show you what happens if I put in 16 first, just to show you what you're gonna see. It's gonna say, no, get your shit together. 16 divided by square root of 18. To 4 decimal places is 3.7712. There we go. Now it still says the same random sample of 18. We need to change our standard deviation to match what we had there. 3.7712. And we're doing less than 260, and notice how it's changed. It used to be 3538, now it's 0558. So they're having you do stuff there. And they're gonna ask some questions like that. Let's look at a couple proportion ones real quick. Get rid of that writing. That's false. Let's find one that actually has some work for us to do. Okay, so here, like on this one, describe the sampling distribution of p hat. Assume the size of the population is 25,000. We need to make sure that 2 criteria are met for a sample for normal distribution. We need to do n times p times 1 minus p. Is that greater than or equal to 10? We have 500 times 0.6, which is our p, times 1 minus 0.6. And if I do that calculation, I get 120. Which is greater than or equal to 10. So that one's met. Then we need to check to see if 500 is less than 0.05 times big N, which was 25,000. $25,000 times 0.05. This right side is 1,250. So 500 is less than 1,250. That is a shitty parentheses, but that's a parentheses. There we go. So we can say it is approximately normal. Because, and we need to make sure we have that formula and this. We need the N is less than 0.05 N. We also need the greater than or equal to 10 for the other one. And that looks like D. Those are the two criteria that we had to meet. And we said this equal P, P was 0.6. And this one requires a calculation. So that is square root of P times 1 minus P over N. We gotta do the square root. So I've got 0.6, 1 minus P is 0.4. That's the 1 minus P. We're dividing by 500 and we're gonna take the square root. Point 6 times 0.4 divided by 500 equals, and I'll take the square root of the answer, and I'm getting to 3 decimal places. 0.022. That's what you're doing on this kind of stuff, okay? One final comment. I didn't say it earlier and I meant to. No, we talked about it. As N goes up, the standard deviation goes down. On the mean. Yeah, we did it all. So your homework problems are kind of like that. You can get the fuck out. Unless you have questions, you don't have to wait. I will stay till 6 if you guys want to work on homework or something. On that, I'll hit stop record.